complex functions. Okay, so we will be talking about the differentiation. We will talking about the analytic functions in complex variables. We will talking about different methods of calculating the integration of a complex variable. Okay, but we will not see the basics of the complex variables. Okay, so the topics in complex variables, the topic in complex variable analysis. This is the subtop. This is the main heading of the topic. The first one in this is analytic function. Second one is Cauchy's integral theorem. Third is Cauchy's integral formula. Okay. Fourth one is powered series, in which two series are coming up. One is Taylor series, another one is Lorentz series. Okay. Fifth one is residue theorem. Sixth one is integral solution using residue theorem. So I'll write solution integrals. Okay, so these are the various topics in this unit. Okay, so we'll take one by one each topic. We'll first start with the analytic functions. Okay, before starting the analytic function, we should understand what is the limit of a complex function, and then the continuity of a complex function. Just like in the normal calculus we have done the limits and continuity, here also limit and continuity exist, but the major difference there between the limit of a normal function and limit of a complex function or a complex variable. Okay, just write a definition. A function fz is set limit L as z approaches z naught if for every real epsilon, where epsilon is a small number, we have positive real delta such that fz minus L lesser than epsilon for z minus z naught lesser than delta. Okay, the basic difference between the ordinary calculus and the complex calculus lies here. See, in ordinary calculus A variable x approaches x naught through a straight line, whereas in complex calculus a variable z approaches z naught from any direction, that is z equal to x plus iy. So depending on whether x is changing or whether y is changing, which gives me z naught x naught plus iy naught, it depends on the path. Okay, but it can follow any path, whereas in this case it has to be a straight line, but here it may or may not be a straight line. Okay, next, this is what the limit. Then second one comes is continuity. Continuity, we can just say a function fz is said to be continuous at z equal to z naught if limit z tending to z naught fz equal to fz naught. Okay, this is at the point z equal to z naught, but there may be cases where a function is continuous in any region also. That means if a function is continuous in any region, continuous in any region of the z plane. If it is continuous in any region of the z plane, that means it is continuous in all the points in that region. Then it is continuous at all the points in that region. Okay, this is a definition of continuity in complex analysis, complex variable. Okay, now we'll see the main topic in this, that is derivative of complex function fz. Okay, now from the definition, if I can write, if fz is a complex function, then d fz by dz can be written as limit delta z tends to 0 f of z plus delta z minus fz upon delta z. Okay, now this limit for derivative of fz to exist, the above limit must exist. Above limit should exist, and it must have same value for all different ways. in which delta z approaches 0. See, originally I am having some point z which is equal to x comma y, and I want to go to some point, say let this be point P and this be point Q, which is equal to x plus delta x comma y plus delta y. Now I can reach P to Q through this way. I can reach P to Q through this way. I can reach P to Q through this way. That means if I am going directly here, then my x and y both are changing simultaneously. But if I am going directly from here and then from here, then I have x comma y plus delta y first, and then x plus delta x, y plus delta y. If I am going through this point and then here, then I have x plus delta x here and y here. Okay, so there are number of ways. There can be some other ways which is not like this and which can go like this. There can be some other ways which can go like this. So there are any number of ways possible. Now my value of the integral, my value of this limit should be same for all the ways. Whatever way I follow, this value should be same. When this value is same for any number of ways, then I can say that my derivative of a complex function exists. Okay. Now that means there should be certain necessary and sufficient conditions for the derivative of this function to exist. Okay. How to find that? How to see what are those necessary conditions? Now see this. I can write my f dash z is equal to f of z plus delta z minus fz upon delta z. Suppose z is made up of x plus iy. Okay. I can assume case 1 z as wholly real. When it is real, then y equal to 0. When this will happen, I should say not z, but delta z should be wholly real. That means delta y equal to 0. That means this time I can write f dash z is equal to limit delta x tending to 0. Now comes a real function u of x plus delta x comma y minus u of x comma y upon delta x. Now before this I should tell that fz is composed of u of x comma y plus I time v of x comma y, where u of x comma y is the real part and v of x comma y is the imaginary part. Fz is my this function plus I time v of x plus delta x comma y minus v of x comma y upon delta x. With this I can write my f dash z nothing as del u by del x plus I time del v by del x. Okay. Now similar thing I can write for when delta z is wholly imaginary. That means only y is existing, other thing delta x is equal to 0, but delta y is required. Okay. Then what will happen? Case 2, delta z is wholly imaginary. Delta x equal to 0, delta z equals to I delta y. So in this case f dash z can be written as limit delta y tends to 0 u of x comma y plus delta y minus u of x comma y, this is related to u function, I delta y plus I times of v of x comma y plus delta y minus v of x comma y upon I of delta y. This is equal to 1 by I del u by del y plus del v by del y. So I can write here as del v by del y minus I times of del u by del y. Let top one will be equation number 1. Let this be equation number 2. Then according to the derivative definition, f dash must be independent of the path whichever it follows. That means 1 must be equal to 2. So when I equate this, I will get del u by del x plus I times del v by del x is equal to del v by del y minus I times del u by del y. Equating the real and imaginary term, I will get del u by del x equal to del v by del y and del v by del x equal to minus del u by del y. These two equations, these two equality equations are called Cauchy-Riemann equation, and these are the necessary conditions for the existence of derivative of fz. Okay. Now we have seen the derivative of fz. Now the real part comes, which is the analytic function. What is analytic function? Its definition and its condition of existence. Write down a function fz which is single valued and possess a unique derivative. With respect to z is called analytic function. Okay, function. This analytic function is also called regular or holomorphic. Okay. The necessary and sufficient condition for this analytic function to exist is again the same Cauchy-Riemann equation, del u by del x is equal to del v by del y and del u by del y is equal to minus del v by del x. Okay, these two conditions must exist for a function to analytic function. Next, let's write one note. A point, first one, a point at which an analytic function does not possess a derivative is said to be singular point. Okay. Second in this is harmonic function. If we take a second order derivative of del u by del x, then I will get, I know this condition, del u by del x is equal to del v by del y. Then if I differentiate this again with respect to x, I will get del square u by del x square is equal to del square v by del y del x. Okay, the second term which I know is del u by del y is equal to minus del v by del x. If I differentiate this with respect to y, I will get del square u by del y square equals to minus del v del square v del x del y. Okay. Now adding the previous two equations, become del square u by del x square plus del square u by del y square equal to 0. Okay. Or del square v by del x square plus del square v by del y square equal to 0. So this is called a Laplacian function or a whole harmonic function. When this condition is satisfied, it becomes a harmonic function. So we can say analytic functions are also a harmonic functions. Now see one problem. We have to find a given function fz equal to log z is analytic or non-analytic. Also find dfz by dz. Okay. First of all, we have to write log z equals to log of x plus iy. We have to separate the real term and the imaginary term. Then how we can do that? We know x plus iy, I can write it as r e to the power I theta, where r equals to under root of x square plus y square, theta equals to tan inverse y by x. Thus log z can be written as log of x square plus y square and y2 plus log of e to the power I theta. This will become 1 by 2 log of x square plus I square. This is the real part plus I times of tan inverse y by x. This is the imaginary part. Now we have got the u and we have 3v. Q equal to 1 by 2 log of x square plus y square, whereas v equal to tan inverse y by x. Okay. Once I have got the u and v, I can find del u by del x, which is equal to x upon x square plus y square. Del v by del y is also equal to x upon x square plus y square. Okay. Now del u by del y is equal to y upon x square plus y square, whereas del v by del x is equal to minus y upon x square plus y square. Let this be equation number 1, 2, 3 and 4. From the three equation, this 4 equation 1, 2, 3 and 4, we will get del u by del x is equal to del v by del y, and del u by del y is equal to minus del v by del x. Okay. Thus Cauchy-Riemann equations are satisfied. Once this is satisfied, it means that this is analytic function. Now it is analytic except at the point z equal to 0. That means at z equal to 0, x equal to 0, y equal to 0, which will make these functions as infinite. Okay, indeterminate. Thus I can write dfz by dz equal to del u by del x plus I times of del v by del x, which is equal to x upon x square plus y square plus I times of minus y upon x square plus y square, which will give me 1 upon x plus iy, or 1 upon z not equal to 0, except at z equal to 0, everywhere it is analytic. Okay, now we will solve one more problem which gives the idea how to find the analytic function. A real part of a function fz is given. See, fz equal to u of x comma y plus I of v of x comma y. Given that u of x comma y is equal to x cube minus 3xy square plus 3x square minus 3y square plus 1. Find the v of x comma y. When v of x comma y is found, we can find the total analytic function. Solution. Okay. U is known. I can find del u by del x. That is equal to 3x square minus 3y square plus 6x. Remaining term will become 0 because we are partially differentiating u with respect to x. Now, according to Cauchy-Riemann's equations, del u by del x is equal to del u by del y. This is equal to 3 del v, sorry, this is del u by del x is equal to del v by del y, 3x square minus 3y square plus 6x. From this I'll get v is equal to 3x square y minus y cube plus 6xy plus some function of x plus some constant, because when I differentiate v with respect to y, this function of x will become 0. Okay, now del u by del y is how much? This is equation number 1. Del u by del y is equal to minus 6xy minus 6y. This del u by del y, this is equal to, according to Cauchy-Riemann equation, minus del v by del x. Thus, del v by del x is equal to 6xy plus 6y. From this, I'll get v as 3x square y plus 6xy, some function of y plus some constant. Let this be c1, this be c2. Okay, now this is equation number 2, this is equation number 3, this is equation number 4. Equating two and 4, I have 3x square y minus y cube plus 6xy plus 5x plus c is equal to 3x square y plus 6xy plus 5y plus c. From this, I'll get 5x minus 5y is equal to y cube, which gives 5x is equal to 0, implies 5y equal to minus y cube. Thus, my v will be 3x square y minus y cube plus 6xy plus some constant. So we have got the v, we have got the u, we have already know the u. Thus u and v will together make a analytic function. Substituting in fz equal to u plus iv will give me the analytic function. Okay, so these are the things, these are the important things related to the analytic function and the way to find the analytic function. Okay, we can expect at least one problem from this topic, from complex variable. Generally, if we divide the whole mathematics, we can see that from each topic there can be up to 3 to 4 marks problem can come in GATE exam. Okay, so this is also important topic.